Have you ever really stopped to think about how your computer or your phone or, well, anything digital actually remembers stuff? It really does seem like magic, doesn't it? But it's all built on one single brilliant idea. So today, let's go on a quest to find the perfect way to store just one single bit of information.
It all boils down to this one question. You see, to hold on to information, a circuit needs to have a sense of the past. It needs to know what just happened. But how in the world do you give a bunch of wires and switches a sense of history? Well, this right here is the core of it. Most simple circuits, what we call combinational logic, are totally forgetful. Their output is just an instant reaction to whatever input they have right now, and that's it. But a sequential circuit, oh, that's a different beast. Its output depends on the current input and its own past outputs. And to know its own past, well, it absolutely must have a memory. So step one on our quest is to build that memory element. And the simplest, most fundamental building block for all digital memory is something called a latch. You can think of it like the original digital sticky note. And here it is, the SR latch. It's this really ingenious little feedback loop. You've got two inputs, S to set the output to a 1, and R to reset the output back to a 0. It's designed to do one thing: grab a bit of information and just hold on tight. Okay, so this is where it gets really cool. If you hit the reset input, it stores a 0. No surprise there. Hit the set input, it stores a 1. Makes sense. But look at that top line. When both inputs are 0, it just holds on to whatever state it was in before. That's the memory. That's the magic. But there's a huge catch. That last state, where you try to set and reset at the exact same time, the circuit just has a meltdown. It's a total contradiction, a forbidden state that we have to avoid at all costs. And that forbidden state actually points to an even bigger problem with a latch. It's always listening. The inputs can change at any random moment, and that means our stored data is super vulnerable and unstable. We need some kind of control here. Which, of course, leads us to the next critical question on our quest. How do we build a gatekeeper? How can we tell the memory, okay, pay attention now, and then, all right, ignore everything until I tell you otherwise? And the answer is the clock signal. This is brilliant. Think of it like a conductor's baton for a huge orchestra. It's this steady rhythmic pulse, tick, tock, tick, tock. It doesn't carry any data itself, but it synchronizes everything, telling all the different parts of the circuit when to do their job, all at the same time. Now, a circuit can listen to this clock in two ways. There's level triggering, which means the circuit is on and listening the whole time the clock pulse is high. But then there's edge triggering, which is way more precise. It's only active for the tiny instantaneous moment the clock changes, the split second it goes from low to high or high to low. And that precision, that is the key. So what happens when you take our simple, kind of wild latch and you give it the discipline of a clock signal? You get the next major evolution in our quest. You get the flip-flop. It's as simple as that. And this one tiny upgrade, just adding a clock, unlocked a whole family of new memory solutions. So first up, let's meet the D flip-flop. The D here stands for data, and its job is just incredibly simple but also brilliant. Its whole purpose in life is to be like a perfect digital camera. It takes a snapshot of whatever bit is at its input, but, and this is crucial, only at the precise instant the clock ticks. And it completely solves that old forbidden state problem. How? With a clever little internal inverter that guarantees the set and reset signals can never, ever be active at the same time. It's safe, it's simple, and it's reliable. But what if we were a little more ambitious? Instead of just getting rid of that forbidden state, what if we could actually make it do something useful? Well, that's exactly the kind of thinking that led to the JK flip-flop, the absolute powerhouse, the multi-tool of the family. This thing is called the universal flip-flop for a reason. It can do it all. It can set, it can reset, it can hold data just like the others. But now, when both of its inputs, J and K, are a 1, it doesn't crash and burn. No, it does something new and incredibly powerful. It toggles. So what's toggling? It's really simple. It's just flipping the output to its exact opposite state on every single clock pulse. If the output was a 0, it becomes a 1. If it was a 1, it becomes a 0. The simple little action, flip, 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 is the fundamental building block for pretty much all digital counting circuits. So the JK flip-flop seemed perfect, right? It's versatile, it's powerful, it turned a bug into a feature. But it had a dark secret. a really critical flaw that would only show up if the clock pulse was a level trigger, if it stayed high for just a little too long. It's called the race around condition, and here's what happens. Because the output is fed back to the input, if that clock pulse stays high, the output toggles, but that new output immediately feeds back and makes it toggle again, and again, and again, just oscillating like crazy during one single clock pulse. The circuit is literally racing itself, and the final state is totally random. A total disaster. The solution to this chaos is an absolute masterpiece of digital design, the master-slave flip-flop. And the best way to wrap your head around it is to think of it like a two-stage airlock on a spaceship. Okay, here's how this digital airlock works. When the clock pulse goes high, the first door opens. The master flip-flop inside looks at the inputs and figures out what the next state should be, but it holds that decision internally. The second door, which leads to the slave flip-flop and the outside world, stays shut. Then, when the clock pulse goes low, the first door slams shut, locking the master. And then the second door opens, letting the slave pass the master's final decision to the output. You see? This two-stage process physically breaks that dangerous feedback loop because the input gets read at a totally different time than the output gets updated. This completely eliminates the race-around condition, and it guarantees one clean, predictable toggle for every single clock cycle. This is it. Perfect memory isn't just about storing something. It's about having perfect control over when that storage can change. So now that we've arrived at this really elegant solution, the master-slave flip-flop, what's amazing to realize is that it's just one piece of a bigger puzzle. All these different flip-flops are so fundamental, they're basically digital Lego bricks. They're all related, and you can actually convert one type into another pretty easily. Now, this slide shows the formal 5-step engineering process for doing these conversions. We're not going to get lost in the weeds of characteristic tables or logic expressions here. The really crucial point isn't how it's done, but the simple fact that it can be done. This interchangeability proves they're all cut from the same cloth, and it gives designers incredible flexibility to pick the right tool for the job, knowing they can adapt it later if they have to. And look, this isn't just abstract theory. These little 1-bit memory cells are absolutely everywhere. They are the fundamental foundation of your computer's RAM. They're the registers inside the CPU that hold data for calculations. They're the timers in your microwave. And they're in the complex state machines that control everything from traffic lights to massive robotic arms. So from that first, simple, uncontrolled latch, all the way to the precision of a master-slave flip-flop, we've really seen the evolution of an idea. This whole journey shows us that so much of innovation isn't just about a new invention, but about taking a brilliant concept and methodically adding layers of control and precision. Every single bit of data in our digital world rests on this long quest for the perfect switch, and it really makes you wonder, what's the next switch going to look like?